Sorry about that, but now we have to finish our discussion of the 12 basic functions. There are three more to go. This is part B. Next up is the cosine function. And it's very much like the sine function. It looks just like it. In fact, if we had just shifted the sine function over about a quarter of a phase, we'd land right on top of the cosine function. We'll learn more about that in coming chapters. But let's just examine this and analyze the function for its domain. Obviously, all real numbers, just like the sine function. Its range toggles back and forth from a minimum of -1 to a maximum of +1 and continues that process. So the range is from -1 to +1. The asymptote is no, it doesn't have an asymptote, but it is, just like the sine function, bounded. Bounded at the top. By a horizontal boundary, and bounded at the bottom by a horizontal boundary. Y equal -1 and y equal +1. And this function, because it exhibits symmetry about the y-axis, you would consider an even function. The next function we'll spend a little time with this year is the logistic function. It's expressed this way, and it has some utility in the area of science and growths of forests and populations, and also decay. We'll spend some time on this a little bit later in the school year. Well, for now, we just want to take a look at the analytics of it. The domain we see is any real number, and the range, it has a minimum value approaching 0 and a maximum value that approaches 1 but never reaches it. The range is from 0 to 1, non-inclusive. We can see from the graph that there are two horizontal asymptotes at the x-axis, y equals 0, and at the horizontal line, y equal 1, which makes this another bounded function. It's bounded on the top and the bottom by two asymptotes. It does not have any extrema, no maximum or minimum, and it's neither even nor odd. There is no symmetry, at least with regards to the origin or the y-axis. The last of the 12 basic functions that we'll have a look at, that we don't work with very much this year, is the greatest integer function. And what the greatest integer function does is it returns the greatest integer that is less than or equal to a given value. So let's take a look. Let's take -1.5. Let's take if x is -1.5, the greatest integer less than that would be -2. So -1.5 comma 2 is on the graph. Let's go positive. Let's say +2.5. What's the greatest integer less than or equal to 2.5? It's 2. So 2.5 comma 2 is on the graph. There's open circles on each of the right ends of these steps, sometimes called a step function. And there's closed circles here. Let's see why. That was the greatest integer less than or equal to 1. Or equal to. That must mean is 1. So 1's on the graph. It's got a hole here because it meets the graph right at that dot. So what is the domain of this greatest integer monster? Well, any real number. We can find an integer that's less than the given one, the given number. So that would be all real numbers. And the range, can you see the range of values? What are all the possible y values? And all the y values are, the integers. And the way to list them is like that. We can see from the graph that the greatest integer function has no asymptote. It's got no extrema. And it's tempting to say it's odd, for if we folded it on the x-axis and then folded it on the y-axis, it looks like it would land right on top of itself, but the open circles would then land on top of the closed circles. And so it is neither even or odd, neither. And that's the last of the 12. What I want you to do with these is know these analytics about them. I could see on a quiz or test asking about name all the even functions, or what are the odd of the 12 basic functions, or something like that. So perhaps a good study aid would be to make some note cards or something for these, so you'll know them pretty well. And that's it. See you in class.